polynomials.
Right. Equations of degree 5 and 6. And these have been, well, famously difficult for centuries, haven't they?
Absolutely. Solving them with standard algebraic methods.
Yeah.
It's often impossible. Think about the general quintic, degree 5. The Abel-Ruffini theorem proved you can't solve it generally using radicals. So finding a technique that can systematically transform these things, that's significant.
And that transformation is exactly what we want to unpack today. We're focusing on one specific tool mentioned in the sources.
The discriminant formula of Morad-Sultan-Ezouidi H-ism.
Right. And it seems its main job isn't just checking roots, but actually computationally simplifying the equation itself.
That's a great way to put it. Think of it like this. You have your starting coefficients. The source calls them Largosses. These are the, let's say, raw inputs.
Okay.
Applying the Ezouidi formula calculates a new set of coefficients, the Sarscow values. And the whole point of this calculation is to find coefficients that define a polynomial with a simpler, more manageable structure, one that we know how to solve.
So lysine in, series out. And the Sori values basically get rid of the computational noise, simplifying the structure. Makes sense.
Exactly.
Okay, let's tackle the degree 5 challenge first. The source lays out a standard fifth degree equation, PS dollars. Looks complicated. 5 terms, alternating signs.
It is. PSX equals by 5, L3 by 4, plus L1Q by 3, L2Q by 2, plus L3Q, XL4Q equals is in a new one. And those initial dorky values, they're a mix.
Yeah, I saw that. Some integers, like the OQ kills a Lun, but then you've got fractions like frac 52 and frac 2. It seems designed to be awkward.
Pretty much. Calculating roots directly from that, a nightmare.
So this is where the Ezouidi formula comes in. It's described as this complex summation process. What's the goal for a quintic, structurally speaking?
Well, the aim is usually to impose a kind of standard or canonical form. For degree 5, a big step is often getting rid of the 644 term.
The second highest power.
Right. The formula calculates the new Zarkal-Ontu values based on how all the initial Q relate to each other. Yeah. It's like it's forcing a certain symmetry.
Okay, so let's see it work. What's the first big payoff when you apply the formula to those messy Q inputs for degree 5?
The very first transformed coefficient calculated.
Yeah.
The source shows it comes out as 0.
0, just like that.
Just like that.
Just like that. CQ equals $1.
Wow. So the 60 Balfour authority term vanishes immediately in the transformed polynomial. That's the simplification right there.
That's a major part of it.
Yeah.
Now, not all terms vanish, but they do change based on the calculation. For instance, 60 acetylase actually ends up being the same as the input, frac 15.
Okay.
But then you get to 2 scalacal, and this one's quite memorable from the source material.
Oh, amidst all the fractions and complex sums, something stands out.
Yeah. The value calculated for 2 CTEs is $113.75.
A clean decimal. Really, $113.75. That feels specific. Does getting a nice number like that mean anything? Especially with all those fractions flying around. It could signal a couple of things. One, that the method is producing a definite, manageable value, not something irrational or endlessly repeating, which you might worry about. And 2, it gives the transformed equation a concrete coefficient that's maybe easier to work with later. The other coefficients, 312 and 60 totalers, are still pretty complex fractions.
Right, I see frac 3253 and frac 3253 before, still messy.
Still messy, but the overall structure is simpler.
So the transform polynomial is now pi 5 plus frac 52 by 3, 113.75 by 2, plus frac 32 5305s plus frac 35 1305 plus frac 305 $3, lost the 6 by 4 taller term, is structurally cleaner, ready for the next step.
Exactly. And that next step, according to the source, is finding the actual roots, the 6 Stola values. This is where complex numbers come into play.
Ah, yes. The solutions themselves. The source gives expressions for them, and they immediately involve things like pi and Esgirl.
That's typical for roots of high-degree polynomials. They usually live in the complex plane. The structure shown for the root 6 conal involves pi pilts, and the imaginary unit $1.
I see the form here. 6k frac Beto 6 plus frac 2.
Yeah. That na raised to an imaginary power involving q Turks is classic complex number territory. It tells you the roots are spread out in the complex plane.
And what about that 197 under the square root? Where does that come from?
That 197 is likely a constant that emerged from the whole discriminant calculation process. It's probably tied to the specific combination of the initial Sertutor values.
So it's like a fingerprint of the original problem.
Kind of. It gets baked into the solution structure. Its presence confirms the transformation worked, leading to a form where we can write down explicit, albeit complex, solutions using standard constants.
Okay, so the formula doesn't just simplify the equation's appearance, it fundamentally changes it into a form where solutions, even complex ones, are computable using known constants.
Precisely. It provides a systematic path from those difficult inputs to a defined solution structure.
That's really impressive for degree 5, but you mentioned the degree 6 cases where this method really shines.
Yeah, I think the degree 6 example in the source is even more striking in terms of simplification.
Okay, so let's look at that. It starts similarly. Px equals by 6, Lq by 5, plus Ln by 4, L2q by 3, plus L3q by 2, L4qx, plus L5q equals net a row. 6 initial coefficients this time.
Right. And again, a mix of values. PQ ready 4, ln cubed, frac 1562, tel q is, and so on. One key detail is that the last input, Wolfger tells, is given a 0.
So no constant term in the original equation for this specific example.
Okay, now apply the Ezouidi formula again. Calculate the transform tool to coefficient.
And what happens? What pattern emerges?
This is the amazing part. The calculation results show that $60, $2, and $7,000 all come out to be 0.
Wait, hang on. $60, S1, S2, S5. That means the terms for 65 5 buzzers by $3, $65 $5 and $60. No, wait. 655 by 4x x squared and $6 vanish.
Let me double check the indices. Yes, it's 7 killers, 2 villers, and 7 tillers that are 0. So the terms $600, 6 by a radasu, by $3. Hold on, the source says $6, S1, S2, S51. That corresponds to $645. The indices might be shifted slightly, notation sometimes, but the point is that multiple middle terms vanish. Let's reread the key result. See the source's conclusion. The values here are $3, S1Q, S to clara S5Q equals S5Q equals $S by 1. That means that 655 for 5 or up $60 is $63, and the 6 color terms are gone in the transform polynomial.
Okay, wow. So 4 terms just disappear. That's huge.
It's dramatic simplification. This really shows the power of the method. It's not just chipping away one term like in the degree 5 case. It's enforcing a structure that wipes out almost everything in the middle for this specific degree 6 problem.
So what's left? Which 6 word are non-zero?
The source gives the non-zero transformed coefficients as 3q's equals 19q's, 24q's equals unto 1 of inches 7, and 6q's equals 1976. Okay, looking closely at the source again. The indices relate to the final polynomial form. The source actually concludes that the simplified polynomial is 2x equals by 6 LW by 3 plus L6q because no others. The non-zero transform coefficients effectively become 3q's related to the 6 equivalent term, and 6 equivalent term, the constant term. Let me check those values again. Yes, the source states 3q 11966 and 6q's are 1977. My apologies for any QS.
Today, we're going to look at a type of math problem that for centuries was basically impossible to solve. We're going to see how mathematicians are creating brand new keys for these incredible equations, taking us way beyond the stuff most of us learned back in school. So let's just dive right in.
Okay, so to really get a feel for where we're headed, we got to start with something we all know, a powerful little tool that probably looks pretty familiar. Yes, the quadratic formula. For any equation where the highest... Today, we're going to look at a type of math problem that for centuries was basically impossible to solve. We're going to see how mathematicians are creating brand new keys for these incredible equations, taking us way beyond the stuff most of us learned back in school. So let's just dive right in. Okay, so to really get a feel for where we're headed, we got to start with something we all know, a powerful little tool that probably looks pretty familiar. Yes, the quadratic formula. For any equation where the highest power is x squared, this thing is like a magic key. You just pop in the numbers, turn the crank, and out pop the exact solutions. It's clean, it's predictable, and you know what? It always works. And that's pretty comforting, right? But it kind of makes you wonder, what happens when we go bigger? What about the equations that are way more complicated? Well, this is what happens. Take a look at this thing. It's a 5th degree polynomial. And let me tell you, there is no simple one-size-fits-all formula for a beast like this. For the longest time in history, finding the exact answers to an equation like this was thought to be completely impossible. This is the mountain we're going to try and climb today.
So how on earth do you even start to tackle a problem that was famously proven to have no general solution? Well, you stop looking for a master key. Instead, you forge a very, very specific one for one specific lock.
And this is our key. It's a specialized formula developed by Murad Sultan Ezouidi. Now, a discriminant is a really clever idea. It gives you critical information about an equation's answers without you having to actually find the answers first. And while the formula itself is, incredibly complicated, what's important is that it was built for one purpose: to systematically pick apart these super complex equations.
And here's the game plan. It's not some sudden flash of insight. It's a methodical, step-by-step process. You pull out the numbers from the equation, the coefficients, you run them through this special formula, and then you just systematically calculate a whole new sequence of values.
It's almost like a complex combination log, Each calculation gives you the next number in the sequence. So, let's see what happens when we actually put this thing to work and start turning that mathematical crank. So, when we apply the formula to that big, scary fifth-degree polynomial, it starts to spit out a sequence of numbers. And this isn't random. This sequence is like a mathematical fingerprint, a signature that is totally unique to this one equation, and it's going to point us toward the solution. For our equation, the sequence kicks off with 0. Then, boom, it jumps all the way up to 115. It dips just a tiny bit to 113.75. Then it shoots up again to 332. And it finishes on negative 443. This right here, this 5-number signature, is a direct result of that equation's unique structure. But here's the thing. This method isn't just a one-trick pony. To show that it's versatile, the research also applied it to something even crazier, a 6th-degree polynomial. And would you look at that? A completely different equation gives us a totally different pattern. Check out all those zeros. The structure of this new problem generates its own distinct sequence, this time ending with 196 and negative 197. It really shows you each unsolvable equation has its own unique fingerprint. Okay, so we've turned the crank. We've generated these unique fingerprints for our equations. We have these sequences of numbers, but so what? What does that actually get us? What does the final answer, the X we've been looking for all this time, actually look like? This sequence of numbers, this is the final key. By taking these fingerprint values and plugging them into another expression, mathematicians can build a brand new formula that precisely describes the hidden roots, the actual solutions to the original problem. And here's one of them. Now, whoa, take a deep breath. Don't worry about solving this. That's not the point here. The point is to just appreciate it. This isn't just a number like 5 or 12. It's this beautiful, elegant expression that involves some of the most famous constants in all of math, like e and pi, and even imaginary numbers. This is the treasure that the map was leading us to all along. So at this point, it's totally fair to ask, okay, this is cool, I guess, but why does any of this actually matter? Let's connect this really abstract puzzle back to the world that you and I actually live in. I mean, really, why would we pour so much brain power into solving a puzzle that most of us will never, ever see in our daily lives? What's the real-world payoff here? Well, it turns out this kind of pure math is literally the bedrock of our modern world. Understanding the deep, hidden structure of equations like this is fundamental to things like cryptography, the stuff that keeps your online information safe. It's essential for modeling the bizarre world of quantum physics, designing cutting-edge engineering systems, and even processing the digital signals that connect all of us. And that's the real takeaway here. The goal was never just about finding 5 or 6 numbers to solve one tricky equation. The real win is forging a new tool, a new key. It's about expanding humanity's mathematical toolbox. And when you do that, you push the boundaries of what's possible in all of science and technology. And that kind of leaves us with one last thought, doesn't it? The entire history of math is just a story of problems that everyone thought were impossible until someone came along with a completely new way of looking at them. It just makes you wonder, what other impossible problems out there right now are just sitting around waiting for somebody to come along and forge the right key?